right, hello and welcome to PodRocket. I'm your host today, Paul, and with me we have guest Alex Bourget. Welcome, Alex.
Welcome. Thanks for having me.
Yeah, we're super excited to have you on because you and your team over at StreamingFast are working on some really cool technology in the blockchain space, and this is a great opportunity to not only introduce some problems in the blockchain space currently to these viewers that we have that are interested in the area, but kind of delve into this next generation of solutions that are coming out and being pioneered by your team. So welcome. And let's start with a little bit about you, Alex. So I know from some GRTIQ podcasts, which for anybody listening is podcast put forth by The Graph. We had guest Nader Dabbit on a few episodes ago to talk about it. So in one of your podcasts, you mentioned you're a classical musician, right?
That's what I studied, right? But I never became an official classical pianist. That's hard. And I wanted to have a family and, pay for bills.
That's important. Yeah. It caught my eye because I'm into piano too. It's really fun.
Right.
Hobby just to sink time into and kind of get away from the world.
But that's my official training, right? Never studied computer science.
So how'd you get into it then? Can you give us
You mean into computer science?
Yeah.
I programmed since I was young. My father had these laptop computers, not portable computers that big, and it was around. So I started programming when I was young, reading books that had basic, those basic go-to line with the line numbers, basic programs on drawings of dragons, and you code a game. So I started quite early, 10 years old, and then I programmed in MIRC scripting, wrote bots and a lot of crazy things. I actually had a first job, was using MIRC as a backend to scrape the web, and then it led on to PHP, Python, and I just had a software engineering career from that point on.
From there, right? So how did you find yourself becoming the CTO of StreamingFast from writing PHP scripts?
PHP 3. Well, I was heavily into the open source world. I had Linux installed on 2 floppy disks, and then something crashed. But I sort of built those computers, so I was really interested in open source. So I've got first job was a consultant, open source software consultant for 5 years. I learned all about Linux and all the ecosystem. And being a consultant, we were thrown in all as experts, in all sorts of situations. So I learned a lot there. Then wanted to go into the startup world. Was attracted by those developing products as comparison to being a consultant. The dynamics. I thought the best would be at products company for different reasons we can go into or not. But so I wanted to join the startup, and then eventually led to the creation of my own startup, a Bitcoin payment processor. That's in 2013. And then continued on tracking I read the white paper at that point, the Bitcoin white paper in May 2013, and think, wow, this is crazy. This could work. And this is in my realm. This is programming money. So I was fascinated. And then it continued on my career. We closed that first business because there was not a lot of Bitcoin transaction volume by then for a payment processor. And then we continued on. I became data scientist in a way, maybe with my current partner, Marc-Antoine, there at StreamingFast. We led in a data science team. His company was bought by Intel, and I was with him leading the data science team over there. So large scale systems, a lot of fun stuff. And then we thought let's go back into the blockchain world because there's a lot of data problems to solve, and we wanted to build some data products, and that's what we're doing today. And that's what's the genesis of what became StreamingFast, I guess.
Heck yeah! I mean, those dots are very clear and they connect, so that's cool to kind of hear that story. So for any of our audience who missed our podcast with Nader, the graph is sort of this technology that's been growing over the past year. And really started a few years ago to tackle the problem of big data and blockchain and needing to index and address that data. So StreamingFast is working with the Graph. Not only are you guys tackling, your own flavor of that problem, but you got a grant from the Graph Foundation to work. So do you think you could start to introduce to the audience a little bit about, again, what is the problem the Graph is solving and how your company is stepping into the playing ring?
Right. So, let me give you a little glimpse of what is, maybe your audience doesn't know exactly what the database of blockchain is, because it's in that category, right? Blockchains, they're databases, and they're particular and they have particular needs, but yeah, that's why the graph exists to index the data that's in a blockchain. But why does it need to be indexed in the first place? Maybe it's useful that I give like a sort of an overview there.
Yeah, please. That'd be great.
So, a blockchain is a database. Like we can compare it to MySQL, but it's master to master replicated, right? And you have one node, you have another node, they need to sync, but no one is sort of the ultimate reference. There's a consensus algorithm that makes sure that the data evolves and everyone agrees, but it's a master-master replication. And there's no, like, if you think of Postgres or MySQL, there's no replication mechanism, right? MySQL has a bin log, and then it can send all the changes to the database to some slave systems, and then you can scale out your read queries. Well, that doesn't exist. Well, that didn't exist. And that's a little bit what we're trying to do here in the blockchain space, because everyone is so, after the fact that they want to scale the blockchain, meaning they want to increase the write throughput. But, the read throughput is left a little bit on its own. And usually blockchains, they want to be so fast at writing that they keep very minimal indexes, very minimal ways to read the data. Like you don't have secondary indexes and columns and whatnot in a blockchain. So you always query through, so most chains today, through a JSON RPC endpoint. And it's very cumbersome, it's very limited. And you query point per point, right? You query for a block, you query for a transaction, and each time it's a round trip, or you query for a data point. You query for inside a contract, give me the balance of that particular user. There's no aggregation. You don't list the users. Actually, on Ethereum, you cannot list the users. The data does not represent a list of users in the memory because it's made for, quickly applying new transactions on top. That's the only goal. So, and also there's another particular thing with blockchains is that they're an eventual consistent database. What does that mean? It means that, you can have, let's say, a block, which is a summary of like inserts and update statements. Okay, you have MySQL, you have a series of updates and inserts, and they're applied, but they might be unapplied. They might be not true anymore in half a second, but it's still useful to know right now, because maybe there's a transaction for $5 million and they convey the intent of someone, your competitor there, that they wanting to trade $5 million or something like that. So you wanted to know sooner than later, because there's always latency involved. That's always a trade-off between consistency, right? If you have something that's eventually consistent, you will be sure about it later. And now you can be aware of it sooner, but not so sure. So it's useful to know sometimes when things are sure. Like you don't want to send your Lamborghini if the 5 millions are not surely, committed. That insert statement for, the payment is not committed. Therefore, we'll call that final or confirmed in the blockchain space. So we wanted to provide systems that give you that finesse, right? And lets you stream the fact that it's real time, but allow you to navigate backwards and undo things that are not true anymore. And I guess, is that useful? Is that something?
Yeah, that's useful. If I could take a moment just to kind of like reword it, right? So in essence, we're saying that blockchain nodes, right? They have a database. That's what a blockchain is. And we can think of the replication between nodes because the whole security point of the blockchain, each node has an exact carbon copy of the data on there. That's what makes the data by block hash verifiable, because any person can go back and verify the integrity of the chain. But the problem is, this is scaled out for security, but it's really difficult to, employ well-known scaling mechanisms to read that data. And otherwise, we're pinholed through the classical remote procedure called the RPC interface, which, as you noted, is very limited. You can't give me the logs for this list of transactions. You can only get one. And it's such a problem that there are some RPC providers that are even selling a service to hydrate the data themselves as you get it. And it's like, I guess that's a half-baked solution, but it really doesn't tackle the core problem, which is there needs to be some framework by which we can scale these reads while maintaining data integrity between our nodes, right?
Let me, tell you another funny, horrible story about what people call when they're getting, because it's an eventually consistency database, eventually consistent database. Well, sometimes you will send a query, a JSON RPC query, and say, give me this transaction or give me this balance for that user. And it's going to respond, and that's fine. And a moment after, you send maybe the request for another address. Okay, you're looking for 2 addresses here. But now you're hitting a different node, right? Because there's no persistent connection there, you're hitting a different node. A different RPC node. Maybe because probably the guy has load balanced his nodes, but they're not in sync at the same time. And truly, within the JSON RPC protocol, there's never a way to make sure you're querying at a given exact place. That's very rare, right, in protocols. So you're connecting to one, getting a response, and then you're connecting to another one. It might not even be the same block number. Like maybe this value has changed 75 times between the two values. But if you want to have, what were the values of those 2 accounts at the same time, you're a little bit out of luck, which is absurd, right? When you want to query a database like MySQL, often you'll say, I want all those, balances, but give them consistently transactional wise. Now we're so far from transactionality because it might even happen that the blockchain over there has the same block number, right? They're both at the same, we'll call height. They have received the same number of blocks, but it happens that this node has block version A and this other node has block version B. They're not the same block. Eventually, we'll purge one of them, we'll converge, and we'll use either block A or B. But you can't know that. So that's really tricky. You're querying real-time systems and you're not sure. So all of the burden of synchronizing and knowing where you truly are is all put on the consumer, like the guy sending the JSON RPC, which in the end goal is like, that would be the browser. But it's crazy because, the moment you augment the number of queries you're after, the greater the complexity of reconciling and making sure all of that is sort of legit. So the other option is just add latency. And then if you query things that are like 10, 30 seconds late, then you can have better assurance. But even then, from time to time, right? So it's crazy to query. But at the same time, it's the only thing that makes sense. These little blockchain database, they have no time for updating indexes. They have no time to update things to make it simpler for you to query because it's not their role. Their role is to process mutations, transaction changes of balance, exchange of money or whatever, as fast as possible. And if they start managing, reading indexes, they slow them down. No one wants that. No one wants to slow the blockchain down. It's already slow, right?
It's a separate problem, right? From the
exactly. It's a separate problem, and that's what we've been tackling.
So the graph kind of takes the approach of saying, well, all right, well, we'll let the blockchains be as fast as possible, and we're going to create a network on top of that of people who want to take that extra time. They can go do this indexing, and they can do it with application-driven, scope from what we call subgraphs. And then they're going to take that data and share it by consumers who want to query that. So
yeah. And one important thing is that the community, like the blockchain itself, has a lot of data structures that are sort of free-form. Like Ethereum, for example, it has a key value. It's a RocksDB behind. It's a small key value store behind for each contract. So you have that namespace. The keys are totally opaque, right? They're hashes of hashes of hashes. Very difficult. They're not easily read. And the values, they're always uint 256, right? 32 bytes worth of data. That's the structure within in the blockchain. Why was I saying that? Is that it has not a lot of meaning in and of itself. Someone like the guy who's writing whatever, an exchange on the blockchain, like Uniswap, something like that. They know how to interpret that data for Uniswap on Ethereum. So they can provide within a subgraph on the graph the intelligence that they know because they created the contract. They created, they know the schema of the data in a way, and they can unpack it and serve it into a more intelligent and refined way for their users. So the graph allows everyone writing to that common database, let's say Ethereum or any blockchain really, which I like to call the social database, where everyone can write. Like, it's crazy, but you never let everyone write to your database. But in the blockchain world, that's what it is, right? You just write and go ahead, but it'll be useful. You explain the schema to people, give them also, views and slices of the data and unpack.
It's essentially little treasure maps about, hey, for this smart contract, what am I going to look for? Like, what little code calls should I track for you?
Exactly. Well said. Treasure maps. So that's what we have in the graph.
So, the graph's really cool, but it still doesn't satisfy everything. And some of the problems that might come up from the beginning of have it being Postgres based are, what do we do when we get to the land of aggregations of saying, I want statistical data? What do we do when we start wanting to scale and make fault tolerant indexing services? And this starts to get into higher throughput and tackling bigger data sets with StreamingFast. And I know this is just the tip of the iceberg, but if you want
Right. There's a lot to be said in there. Well, the graph did one thing very great, is that they made an end-to-end solution, right? There's a blockchain extraction layer, and then you provide some WebAssembly or assembly script code that takes that blockchain data, interprets it, transforms it into a beautiful set of columns and values, right? Floating point and all that. And then it writes it to Postgres, and it allows you, not only that, to query it using a GraphQL interface. That's a nice, simple end-to-end solution, and it got there. Now, obviously, like it gives some, let's say, it informs the way the schema is written. It's written in a very particular way, right? Because it allows you to do time travel queries. What was the state of the previous block and all that? So it imposes a structure. And also it's, it doesn't do all the things at query time, because the database Postgres is laid out in a particular way. And you don't have a lot of flexibility because you're saving really rows and entities. And then you're taking, the language that is exposed to you, which doesn't include massive aggregations and things like that, really. So that's cool. And let's say, maybe I can tell the story of how we got near to the graph. Like, we looked at that model, and we were building some streaming solutions for many years.
Just to clarify, streaming the raw block data from the node.
Well, yes. Our goal has always been to take that blockchain data, extract it into something more streaming than polling. I hate polling. Everyone at our place, we hate polling. So we wanted to transform those blockchain nodes into a streaming solution, and we've built things. What do you do with data? You index it. What's the purpose of a database if not to read it, right? Well, we made sense out of it. So we created systems to search, index, and all that. So similar to the graph in a way, right? And at some point, we looked at the graph, that end-to-end solution, and we applied our technology, our streaming technology, to one of these subgraphs, and we made it 800 times faster.
Oh my God.
Yeah, it was just like crazy. And then I think got on the radar. We knew the graph people a little bit, but I think that was a little, So that was really nice, and it really proved some facts about the power of the streaming solution. And then we joined the graph, which is a funny story too, because it's sort of I have never heard about that, like sort of a company, not acquired by, but sort of joined to, or, adjunct. I don't know how to say that. We're now a core dev team of the graph aside the other core dev teams. And we've received a large grant that allows us to continue doing that sort of, for full time for the next years. So we've been aligned, not acquired. We've been, I don't know. So Web3 acquisition, someone would say, right? It's fascinating to go through that.
Decentralized version of acquisition.
Yeah, exactly. Funny.
So what I'm curious is, can you share with us what that subgraph was and what type of data was it serving? Was it something giant like the sushi one, or?
The funny thing is that, why we attacked that, because we saw an opportunity. The subgraph that was slow was the pancake swap one. It was running on the Binance Smart Chain, and Binance Smart Chain happened. So, the speed of a blockchain is what we'll call its block time, right? You have a thing that can settle transactions at each 12 seconds, like Ethereum does, something like that. You have some chains like Solana, 0.4 second. So that's, let's say you're in MySQL, you can sort of commit things each 0.4 second. That's how the consensus worked, right? Before everyone has agreed upon, 0.4 second has passed for Solana, 12 seconds for Ethereum, Bitcoin, like it's 10 minutes, has different properties there. But BSC is 3 seconds. And BSC, the Binance Smart Chain, the one where PancakeSwap is, which was really going up like a trending, a lot of volume, a lot of trading happening on that, a decentralized exchange. Well, there was just, and also the chain was sort of squashed to push out more and more transaction each block. So the throughput was, I don't know, like 20 times more than what you see on Ethereum, and much faster also. And they started having hundreds of thousands of trading pairs. And that particular setup on on the normal, the base, graph node, the technology by the graph there, it was grinding to a halt. It would take 4 seconds to process a 3-second block. So it was just never going to sync. And we were looking at it, it was syncing before 2 months and with no end in sight. So that's the one we took. We sort of transpiled with our technology and infused it by streaming. And we always also strive to make things parallelizable. That's something really important I learned from data science. If you don't make your things parallelizable, if you don't try to leverage the horizontal scaling capabilities of your computing stuff, like cloud instances or whatever, well, it's always going to be longer and longer. So we made that thing parallelizable. So we were able to shrink it down to 6 hours. What was no end in sight? So maybe the ratio, I say 800 times. Really, it's when you divide by eternity, you get some big numbers. But so yeah, by making it parallel, that's always been our design principle. Put data from the blockchain into files. Maybe I'm introducing a little bit of the Firehose here, right? So extract data from the blockchains, put them into files, because files can scale horizontally. That's what's used in the industry, right? You launch a bunch of machine, Amazon S3 or Google Storage or things like that. That is known to scale. So you can run a lot of machines in parallel and they all crunch their own segment and provide, the results. That was our approach, right? And that made sense, provided that we extracted the data and turned it into files. So that was one of the big difference, I'd say.
So sort of to explain the benefit to the operator here that you guys kind of brought with speeding up the subgraph, for any of the viewers that are, not so familiar with the graph, the task of the indexer, right, for one of these subgraphs is to look at any number of entities being emitted by that blockchain, write them down, index it, and get ready to serve it. So for something like PancakeSwap, the more pairs there are, the more amount of things you need to pay attention to as an indexer. And then furthermore, we highlighted the short block production time meant that more of those pairs just got emitted faster and faster than you could ever want on Ethereum. So from a typical person indexing this data, sitting and running the graph technology and waiting for BSC blocks to come in and writing down their indexes, how does that change? How does that little ceremony of events change when they use your technology?
So, the original graph implementation was turning around each block and doing some JSON RPC requests. What does it have as an option? It's just, that's what they do, right? So they would go and query like crazy and just saturate one node and then 2 nodes and 5 nodes to extract some data that is in a wrong format, right? It's in the RocksDB. So it's because you need to extract it, and by querying these transaction by ID or block per block, well, you need to do a lot of round trips with all the funkiness that I explained earlier on. So you need to account for that, and you need to send requests. That's annoying. Whereas the technology we brought in was a flip side. It's pushing data to you rather than you pulling with requests. It's pushing more data, all of the data that each block produces. But in the end, when you get it in memory, it's much, much faster to filter and do whatever you want. And it's ready to be processed, and you'll get pushed the next block after. So there's no network round trip, really. I like the image of, tent poles. Tent poles, you put them, you stitch them together and they click, and you have that 2 inches of, of things entering one another. So you have the large tent pole and you push on one side and whoop, and it pushes directly on the other side, right? Our streaming tech, we like to see it as it pushes from the blockchain directly into your app, even though there's a few legs of network hops, right? It's push from end to end.
beauty about the file, the whole concept of files, that's the most basic element in a Unix system. That's like, if you boil it down to a file, the options become limitless. Like, you can even throw a simple Nginx thing in front of that if you wanted to.
Yeah.
So,
Caching, peanuts.
right. It's just the possibilities become endless of how you might want to scale or like load balance that out.
Maybe it's not so clear because I'm talking about streaming and we're talking about files, but so that's the thing, the blending of these two things, because we have a source there that is deterministic data. It's a blockchain. You run it again from the beginning of history, it'll produce always the same data. Like, in a sense, it's sort of a logs-based architecture, right? Similar to Kafka, but it has the property that you can always reprocess it from the beginning, and it produces the exact same deterministic output. So that, if you can put your hand on that data extracted once, you can put it into files, but also you can stream it real time. And that's what the Firehose does. It extracts it real time, puts it on disk, and the next time you need it anywhere in the history, you start from the files, you load them, and then you can stream them at high speeds because you're really sourcing from flat files, easy. And then you can switch to live mode, because blocks have that sort of general clock, block numbers and hashes. You can easily sort of switch from files then to the live stream. And so it's, from a consumer's perspective, it's just one thing, one powerful streaming engine backed by files that you can cache and on which you can do parallelized operations on.
And if any of the listeners are interested to read more about the Firehose, Alex and their team actually put out a really great RFC with pictures in it, right? And we all love pictures. So we can put that in the link to the podcast if you're interested to read that for yourself and check it out. So yeah, to summarize, it's like the Firehose is providing a framework to stream block data that is a push interface instead of polling, which also commits it to disk, and it allows you to go between the live mode of being streamed blocks and reading flattened data from that blockchain at a very high speed because it's flattened. So on the topic of flattened, right, if for anybody that's not into, data, can you explain a little bit about what that means? Like, what is a flat file in the context of this domain?
A file is a file. You know what the LS on your system, you'll know what a file is. But what is particular about that data in those files, I think it's very important or particular to our systems, is that we extract from the blockchain nodes more data than is actually available through all of these JSON RPC combined, right? Because we go, and so that's our approach. We saw that the JSON RPC endpoints do not provide all the data that is needed. Let's say you can get a transaction, but in the transaction, you don't have a clear view of those nested calls, like function calls that call one another and all that. And that's funky in a blockchain because you're calling someone else's code, and then you're calling back. You can have a call tree of different contracts written by different people. Think of stored procedures by different, authors, and then yours calls theirs and whatever. And you have a lot of useful context. But normally you get the JSON RPC, you get only events that are flattened and don't give you that context. But in many situations, it's really useful. So we thought, we're going to go to the source. We're going to modify the blockchain nodes. We're going to pry open the MySQL source code, right? How often do we do that in life? Open the database's source code. So we did that for all the chains. So we can go literally put printf statements in there, okay? And that's like, let's imagine printf, right? To output the data as it's being produced, as it's mutating its storage. Like, think if you were in the middle of that insert statement in MySQL, well, you could read the data that was there before, or an update statement. You could output what was there before and what's the new value, and output all these deltas. And that's also been really useful for us. We always wanted to have the deltas out so we can know what was before, what is after for any change that occurred to the database. And you don't have that in JSON RPC things. You don't have that. You don't have that in context. So we went there and extract so much more rich data, contextual and contextual data. And that's what we put in those files. So it's so much richer. And then you can start expanding on that and interpreting the data, because often it's just series of, events. They all look like series of 32 bytes. If you look at that, you vomit, right? Coming from a MySQL land where everything is typed and all that. So, but with that and some intelligence of the contracts, you can now, extract more meaning. And that's what we put in files. And that's the same thing we put in the live stream there. all, just to be precise, they're all protobuf models of the blockchain's data, the most complete definition of the data in those blockchains. I haven't seen anything more exhaustive than the protobufs that we output for each of the protocols we support.
And the way that you do this is by taking the node, as you said, taking a big crowbar, you wrench that guy open, you say, we're going to put in little spies in here to grab information and just barf it out.
Exactly. As fast as possible. The design principle, least impact on its write cycle, right? Because you want to have the max performance. Output it as fast as possible. If it's hex, let it be hex. If it's protobuf, let it be protobuf. The fastest to get it out, because then you get into that read land. You have tremendous power outside of the blockchain node to organize the data, rethink it, reshuffle it, decode it from hex to whatever, or protobuf, or whatever, Avro if you want. And then push it out for read consumption. And then you can imagine the limitless read system. You send that out to a Postgres that has an index, to a key value store, to whatever other systems. And now you can shape it to make it ready for query, but in all sorts of dimensions that you can never ask the blockchain node to do. There's so many ways to ship, pivot data.
And just to show, I guess, in the case of example, how powerful this concept is, this can make data that would otherwise be like ludicrous to say, oh, we're going to like keep track of everything, such as Solana.
Yeah.
Like now we can think about it being accessible to people everywhere to take in that data. And just the difference in scale. You said BSC does a block every 3 seconds. Ethereum, which we consider decently fast by modern standards, is one every 12 seconds. Solana is one every 400 milliseconds. So that whole new playing field. And there's a lot of internal transaction noise. If anybody here is into Solana, there's a lot of stuff going on inside. So taking in that data and the fact that the Firehose can do it really goes to show how effective the solution is.
Right. We built our technology on fast chains. We started on the EOS.io technology, right? And that was already a thing that could do 4,000 transactions per second with a block time of 500 milliseconds. So quite fast and a rich, introspectable data. And that's what we built and scaled. So when we arrive even to, Solana has a lot of throughput too, but like Ethereum was really a small thing aside, right? And some slow chains like that. So it's ready. It was designed for, large scale systems. And, like when you design large scales, think in Intel. We're developing systems that we're shipping on 200 million machines per year. Is that correct? 200 million, like the software, and we would do some analysis on the behavioral, when did people open the app and whatnot. So a lot of event streams to behavioral analysis. In that case, your throughput can grow, double. Like you ship new machines, the throughput always grows. And so that's what I would say the Web 2 systems are designed to do. In a blockchain, your throughput is limited by the blockchain, right? It's deterministically from that point on. It scales with. So it's actually not so much data by, today's standards in big data world. But we need a system with particularities, like the thing that, for example, navigating reorganizations, like eventual consistency, flushing and killing of some blocks that are not true anymore. And that's another, I think, crux of the features in Firehose, that it helps the end user navigate reorgs in a, cursored way. We provide a cursor so you can disconnect, come back. We'll always continue linearize sort of the wonkiness of the eventual consistency and give that guaranteed downstream, which is totally non-existing with other solutions. And that simplifies the work downstream, right? For anyone consuming blockchain data, our customers usually said, I was able to cut down 90% of my code reading the blockchain because of that. That's what I want to hear.
Yeah, like firefighting, you don't have to do downstream because it's done by the fire hose. Oh, wow. I didn't
exactly.
That there. What do you know? Puts out the fires. Did the name kind of come from the fire, Kinesis fire hose kind of mindset?
It's a fire visually. It's a pipe and then it's streams all the unfiltered, right? The original close to the node, it has a pipe with all the things in blocks, all the data. So it's like I'm thinking of the Twitter Firehose. At some point they had that product. It would just send all the streams of all the tweets. So you could pay for that. I don't remember. So yeah, the image is fitting, I think.
So We kind of discussed the Firehose and StreamingFast in the context of the graph and how it's going to empower, new types of data indexing for it to be done on a larger scale, to have it, more fault tolerant, scalable horizontally. What other applications or areas and domains do you think that this sort of paradigm shift of how you index and take in data could maybe foster other application growth? Have you put any mind to that, or have any?
Man. So, for the last year, we've been thinking of how to parallelize subgraphs, because we had made that proof of concept that we could turn it into something 800 times faster. So that's been in the back of our minds all the time. We're sort of brought in to bring performance to the graph. And the way we had done the first one, that pancake swap the project was called Sparkle. We took exactly the code written in assembly script from that group over there, Pancake Swap. We transpiled it and we sort of fitted some layers of stages of execution to make it parallelizable, but really wasn't designed for such a parallelism. It's designed for linear processing. And a subgraph today, you need to start from the beginning of where you want to track transactions, and then it's going to go linearly, and you have to process 5 billion transactions before you get to real time and what's up right now in the chain. That's cumbersome. So we always had that in mind. So right now, this is pretty edgy. I haven't announced. This is pretty. It's not a fully formed idea. It's in design. We have prototypes. I think it can have a huge impact in the graph ecosystem, but also elsewhere. We're taking that streaming aspect and giving it a possibility to have small, I don't know if you guys know Fluvio. They have smart modules. It's a streaming engine, right? It's a streaming engine, takes some things, you write a bit of code there, and then, bytes in, bytes out, you can transform it, you can do stuff, filter, map your storage and your events. So the technology that we're sort of doing, I'll call substreams as a code name, but takes the Firehose, allows you to provide those small smart modules, similar to what we have here, WASM modules. And then we can start composing in streams fashion. So we're far further about, the Postgres aspect of subgraphs, where Postgres is a given, right? It's part of the deal. Here, we're allowing people to go and compose streams and feed. And also, because we have a clock, because a blockchain has a clock, right? We can actually synchronize multiple streams together to fuse data and create incredibly composable streams of data that are really public, that leverage the intelligence from the Uniswap team to make sense out of the blockchain data and give it a stream of prices, and then another stream of trades, and another stream of I don't know what, right? But they're all small nuggets of intelligence from Uniswap. And then what? Like SushiSwap can do the same thing. Uniswap, and they can all provide those small nuggets. And someone can go then and compose, let's say, an average price across all these DEXs, right? DEXs mean the decentralized exchange here. So the price from that guy, and you can start seeing something really powerful that can end up in a database, but probably you're not forced into putting it in a Postgres database. You can put it anywhere. And it still has all those properties of reorganization, dealing with, eventual consistency, because all of that is eventually consistent because your source is eventually consistent. And it has all these same crazy properties of parallelism that you can, if you have a small, a mapper, it takes a block, outputs a series of pairs or trades. That's totally parallelizable. So we can leverage the fact that it's files-based, like we do in the industry, take files, spit out files, right? Transform, spit out. And so, yeah, I'm really excited about this. Is sort of on the edge of the design space, but we have prototypes and I think it's going to have a huge impact.
Just for imagine being able to say hey, I want to stream this complicated data, and there's somebody out there that has a substream that you can make some sort of arrangement with to pull that data from. That would be wild. Because
exactly. And you know what? Let me pitch the further story. What I'm imagining there is that you have a pool of resources. And here we're getting close to BigQuery. For those who know, BigQuery is a large-scale distributed system. You send a query, and it's going to do your things in parallel on thousands of servers, and cobble them up and bring up your response. Right? It's a large-scale SQL system. Well, I'm imagining that we could do that with substreams. Well, you'll send a sort of specification of the stream you want, and you send it out to that ecosystem of indexers in the graph, and they'll process the chunks that they have. They'll leverage the files that they have if they already processed it, because they're common things reused by a lot of people. And then it can distribute the works, do it in parallel for when it makes sense, and then accelerate things and then like reuse massive resources to even create a query time. You'd write a little bit of code and you'd inject it, and it would be a query time processing. Like you'd be querying the pool of streams real time. I don't know. I think it's pretty exciting. I think it can be a side of a big query engine, like a pool of all blockchain data that is queryable through streams, and you can just send in your WASM defined query if you want. And leverage the community, leverage the intelligence that everyone has put together. That's the crazy bit, because you don't want to do that alone, analyzing Sushi, Pancake, and all these protocols that have crazy ways of storing their data in their contract. No, let them do that and just take the sweet, refined, streams up there.
It's really leveraging the decentralized economy that's being built right now. So we're running up on time here. I know I could keep talking. I want to ask one selfish question that's been brewing in the back of my head though. So I know that, and correct me if I'm wrong here, but the Firehose is sort of based off of the GETH and the Open Ethereum client. So do you see StreamingFast, because of the way you're approaching flat storage, eventually making technology like Erigon not as relevant anymore? Because the whole thing of what you guys is, wow, we don't have to traverse this whole partition tree and RLP things and like look at it. But Erigon says it's flat already. We're done. So how do you see you guys playing with Erigon and that tech?
So for us, you said we've started. So the truth is the Firehose is an agnostic system from any blockchain in particular. For Ethereum, we dug into Geth, the Go Ethereum code base, and we put print statements. And then for Open Ethereum, which is another implementation of the same protocol, Ethereum, we went in there, it's in Rust, and we put some print statements. In Argol, we do the same with Erigon. We haven't done it yet, where it's based on Geth, so the patch is very similar. But our goal is to extract the data from those protocols in an agnostic way. We don't care which of those servers you're using, because the protobuf that gets out of a block is deterministic. We're talking about a decentralized system that every node needs to agree. So the data that gets out is by definition deterministic. So once we get it out of a node, we don't care how the node stores it. We have it all here. We can lay out in like a million ways. So the way Erigon stores it helps Erigon accelerate its own internal use, because it's not going through 64 queries on the key value store, but rather just one. For some reason, akin to the decisions they made over there in Geth originally, whatever. I don't really care, because if Erigon is fast, I can get the data out fast. And then we're out into the blue ocean of possibilities, right? Using that data. And if I want to put it flat somewhere, I'll put it flat. If I want to put it convoluted, I'll put it convoluted if it's useful for my use case.
Really? So gotcha. So it's really like a complement of saying like, we're here to adjust to all the different clients depending on
we don't care. If there's deterministic data, we'll spew it out. That pattern works on all chains we've tried. It works in a sort of systematic way. You have a thing producing data linearly that can be eventually consistent. That's the only thing the Firehose needs. And it's agnostic of the payload that is, EOS specific or Solana specific. Doesn't care.
That's awesome. It's going to allow the scaling out of the domains to be quick. Yeah. Okay, Alex. I could keep talking, but I know we're up on time here. So thank you so much for coming on. This has been a great session. I am happy to help spread the word of the Firehose and the graph at any given moment I can. So thank you, PodRocket, for letting us delve into these topics. And is there any sort of like documentation or areas you would like to put in or mention for the audience on your behalf or for their own knowledge seeking?
Well, if you want to reach out to us, go to our website, streamingfast.io. It has almost nothing, but you can join our Discord community. You can go to the Graph Discord if you want to speak to us in particular. Our Discord is the place where you'll reach us and we can chat about things. We're working on having some large scale docs for all the chains and how to deploy all these things, because it's just recently sort of packaged for the graph. So it's not all there already, although it's usable and people deployed it and you can consume those streams today. So go to our Discord. That's the best thing you can do if you want to keep in touch. Or in Twitter, streamingfast.io. Hey, thanks a lot. Thanks a lot for having me.
Thank you.